Good afternoon. So let us start this lesson. This is a very important part of this course, the notion of metric spaces. And then again, these are the notes that I have already uploaded. The formats are a little bit different, but you should just need to follow these numbers. For example, definition 3.1 aligns exactly with the ones that I have uploaded on Canvas. So if you want to write less, you can have them in front of you, any way that you are comfortable with. Okay, so the thing that you see here, topology of the real line, of course, this is the title of this chapter in your book, but we are not talking about topology. Okay, these kinds of properties that we are going to discuss in this chapter is called topological properties. So what do we mean by a topological property? It means that we want to impose some kind of a structure on an abstract set. An abstract set is just a collection of objects. What are these objects? They could be anything. They could be numbers, they could be things, they could be matrices, functions, and anything you can imagine. And now we want to put a structure on the set so that we can understand how the points are close to, are 2 points from the set, are 2 elements from the set close to one another or not. It turns out that the most rudimentary structure that you can pose on a set so that it enables you to talk about closeness and farness, if the correct English word, farness? Distance. Distance, yeah. So if they are close or they are far from one another, it turns out to be a topology. Okay? But then we are not going to talk about that. We want to put another structure on an abstract set, and we call it a metric space. So I just want you to know that topological spaces are the very basic underlying of any kind of structure that you can pose on a set to be able to talk about the distances between the points. But in topology, you cannot actually measure the distance. You can say which points are closer to one another with respect to the others without exactly knowing what the distance is. But in analysis, we prefer to be able to talk about distances as well. So, but before doing that, there is some part, for completeness, I have written it here, but I don't think it is wise to go through them because there are many important things we have to know. So the notion of absolute value, hopefully you know, and these are the properties, famous properties of absolute values. So hopefully you know them. But this thing is important. Some of you, I hope that everyone knows about triangle inequality, but if you don't, I want you to remember that. So the absolute value of a sum is at most equal to the sum of absolute values. There is no guarantee that these two quantities are the same. You can also prove that this equality happens if and only if x times y is a non-negative number. Okay? So, and there is a very important consequence of this one, which I want you to know. So let me, for example, if you have absolute value x minus z, you can write it as absolute value of x minus y, any chosen number, and then plus y minus z. Yeah, so that's understandable. But then, this is a sum, absolute value of a sum, according to triangle inequality, becomes less than or equal to the sum of the absolute values. So from now on, if I need, I can immediately write that for you. So yeah, you should understand that. Any questions? It's very simple. So absolute value of x minus z is always less than or equal to absolute value of x minus y, any chosen number, plus absolute value of y minus z. And one more thing that I want you to know is that the absolute value of the difference between two absolute values is at most equal to the absolute value of the difference. It's a consequence of triangle inequality. Okay, so this is something. So the distance between two absolute values is at most equal to the distance between the values. So for example, if you want to understand that, so absolute value of x can be written as, for example, absolute value of x plus let me write minus y plus y. Yes, they are the same. But now I have a sum. The absolute value of a sum is at most equal to the sum of the absolute values. Absolute value of the first one, if you want, I can keep them together, and then plus absolute value of the second. Yes, and then you can move this to the other side, and then you get absolute value of x minus absolute value of y is less than or equal to absolute value of x minus y. And then you can also do something similar, but instead of starting with absolute value of x, you can start with absolute value of y and do something similar. You will see that this one is also greater than the other way around. So this means that this is valid. Okay, so if you want to combine the triangle inequality and this one, I haven't written it down. Oh yes, I have written it down. So you can write it. So that's the most general inequality that you might need. Okay, any questions so far? Okay, but now let us go to the main topic of today's lesson, abstract metric spaces. So what is a distance? So distance is a number that you associate with 2 points in a space, the normal distance we have. So if I want to talk about the distance between 2 points, I have to give you 2 points, and then if you have a measuring tool, you measure the distance between them, but what do you give in return? You give me a number. Yes? So distance is a function that takes 2 points from you and it gives you one number back. And that number cannot be negative by the expectation we have from the distance. It's a non-negative number. And then we know that 2 points, if the points are the same, the distance between them is 0. Or if the distance between 2 points is 0, what can you conclude? You can conclude the points are the same. Yes? And then you know there is no difference between the distance from point A to point B or the distance from point B to point A. They are the same. Yes? So these are these are the ideas that we have from normal distance function. Okay? And there is one more, and that is called triangle inequality. Yes? So what does it tell me? It tells me that, so exactly, if you have 3 points in a space, okay, so the distance between these 2 points is less than or equal to the sum of the distances from this point to this and from this point to that. Okay, so this is something that we know. So I'm not saying that, so these are the properties that the usual distance enjoys. And now we want to abstract them out and say that, okay, I want to define a distance function, which is called a metric, on an abstract set X. Okay, so how do you define a metric? Okay, you say that a metric is a function that takes 2 points from your set. So it means that it takes a pair from the Cartesian product of X by itself and gives you a number back. Okay, that's the meaning. So when I talk about a distance function, or the terminology from now on will be a metric on a set, which of course I assume from now on that the set is not empty. So if I have a non-empty set, but any abstract set, a function defined on the Cartesian product of this set by itself to the set of real numbers with more properties is called a metric. The first property is that, so let me write x and y and z are in X. The first thing is that the distance between x and y is non-negative. Okay? We are imposing the property on D. If D enjoys all these properties, then it means that this is enjoying the same properties of a normal distance. Then it is plausible to also call it a distance. That's the idea. The second thing is that if x is equal to y, then the distance between x and y is 0. And the other way around, if the distance between 2 points is 0, the points should be the same points from the set. Okay? So these are axioms of what I want to call a metric. So number 3, the distance from x to y is equal to the distance from y to x. Okay, and finally, this type of property. So number 4, d of x and z is less than or equal to d x and y plus the distance from y to z. So if I give you a non-empty set, and if I give you a function with this structure, whose domain is this set Cartesian product by itself, and the codomain is the set of real numbers with all those 4 properties simultaneously satisfied, then I would say D is a metric on X, and the ordered pair of set and this D is called a metric space. Okay? So in other words, if I just give you a set, I don't know, for example, if I just write you a set, okay, so let me put some strange symbols. So for example, let me just do something like this. And then if I ask you what is the distance between this A and this upside arrow, it's nonsense. It's a nonsense question because there is no structure on it. But as soon as I define a metric on this set, a function with these properties, then I can talk about the distances between any 2 points of the set. Is that clear? Understandable? Okay. So let me also go to the next slide. So each axiom has a clear intuitive meaning. We talked about that. Non-negativity means the first one is called non-negativity. Means the distance between 2 points cannot be negative. Positive definiteness. This property is called positive definiteness. Okay, so positive definiteness, what does it tell us? It tells that the only point at distance 0 from x is x itself. Symmetry means the distance from x to y is the same as the distance from y to x. And triangle inequality, going directly from x to y is never longer than taking a detour through z. Yes, that's the intuitive meaning of these axioms. Okay, but these type of questions, I have given you this function and I'm asking you to show that this defines a metric on R. And by the way, this is not surprising, yes? Because if your set, so I want to example 3, so let me just write 3.7. So the set, underlying set, or sometimes we can say the ambient space, X is R and D is defined from R to R again. How? D, X and Y. So in this language, X and Y is coming from domain. So this means X is coming from R. So X is a number. Y is also coming from R is also a number. The output is usually always should be a number, and the number is defined in this way. Okay? So we want to show that this function is a metric. And this is not surprising because that is the same usual distance in the step. So if I give you this and I give you 2 points an x and y on the R axis, and if I ask you what is the distance between them, so you can exactly calculate this. Okay, but if I want to do it abstractly, I have to check all 4 properties. Okay, why this is a metric? So number 1, so dx and y, so I would say let x, y, and z belong to R. Then, so number 1, dx and y, according to the definition, is absolute value of x and y, which is greater than or equal to 0. So the first one is satisfied. Number 2, do you agree that if x is equal to y, then absolute value of x minus y becomes 0? And this means that dx, the distance from x to y, is also 0. And hopefully you can see that this is also reversible. So number 3, it's extremely simple, yes? So number 3, dx and y is equal to absolute value of x minus y, but you can write it as absolute value of y minus x, and this is the distance between y and x. So symmetry is also satisfied. And number 4, so this one is number 2. Yes, let's not write it like this. So number 3 and number 4. So number 4 is on the board. Yes, so dx and z is equal to absolute value of x minus z, but this is exactly on the board here. Yes, absolute value of x minus z is less than or equal to absolute value of x minus y plus absolute value of y minus z. But what is this one? This is exactly d of x and y. And what is this one? This is d of y. Yes. Of course, this is not something very interesting because you already knew that this is the normal distance. So the normal distance should be indeed the distance, a metric. So this is the idea. And the hard part usually is this part. It's not that easy usually to prove this for any given, arbitrary metric. Any questions? Okay. So this one, I really want you to have it in your memory. This is a very strange metric. So, and this is important. I give you, let me just explain it here on the board. So 7, 8. X is a non-empty set. This is important to know. I am not imposing any structure on X yet. X is just a set of random elements, random objects. They are not even numbers. I don't know anything about what is inside X. But I am claiming that this function defined by this strange way, this strange formula is a metric on X. Yes? So this is a very strange metric. So if I give you 2 points that are not the same, the distance between those 2 points is always 1. So, but you see that this is a string. So it doesn't matter if the 2 points are here or the 2 points are here. The distance between these 2 points is defined to be 1. The distance between these 2 points is also defined to be 1. Okay? The reason that this is extremely important in analysis because most of the time you are inclined to think intuitively based on the Euclidean space that we know about it, and then you get some kind of wrong conclusions about the general metric spaces. So whenever you want to test your intuition, this is a very nice example to have in mind. So if you have some intuition that, okay, in general for a metric space, this rule should work based on your intuition that you have from normal Euclidean space around you, then it is better to test it with this one to see if what you are saying is true or false. So knowing this metric is important because of counterexamples or counterintuitive examples that you might come up with. But for example, do you agree this is a metric? Because here I knew about the underlying set. The underlying set is familiar to me. It's just a set of real numbers. But here the underlying set, I don't know anything about it. I just know it is a non-empty set. But I am claiming that this function, always is a metric on any unknown set which is not empty. For example, I have to check 4 axioms. And non-negativity is clear because I see by my eyes there are 2 outputs, either 0 or 1, so it is non-negative. Okay? Do you see that this is positive definite? Yes? Because this meter, this value is either 0 or 1. It is 0 if and only if under one condition x and y are the same. So that's positive definite. Yes? Is it symmetric? Yes, because if x and y are not the same, the distance is 1. If this is the same, the distance is 0. The other way around will be also the same. Yes? And then if you want, you have to also check triangle inequality. So I will ask you to do that. So the only non-trivial part, which is extremely simple, check number 4. Okay, so it's extremely simple. But remember it from now on. Okay, so remember this. Could I define it the other way around? Could I define it 1 for x equals to y and 0 for x not equal to y? No, of course, because according to the definition, when x is equal to y, any metric should give you 0. So I could not define it the other way around. I have to, if I want to define it, this is the most reasonable way. Okay, so when I am reading this metric defined in this example is called a discrete metric. So I will use this word. In this space, any two distinct points are exactly 1 unit apart. Okay, this example is particularly useful because it demonstrates that the metric does not need to arise from geometry in the intuitive or Euclidean sense. It only needs to satisfy the formal axioms. That's important. Okay, so example 310 is a long one. That's why it becomes like this. So I will not have time, of course, to go through all these metrics, but I want you to understand. So if you really want to show that all these things that I have defined for you is a metric, you have to go and prove all these 4 parts. So for example, here, instead of having, so let me write which example was that? Example 310. So let me just try to understand it a little bit. So let us say that the underlying set is R2, R squared. So if I want to define a metric on R squared, what do you expect? You expect that this should be from R squared times R squared to R. Okay? So the first one that I have defined is just a normal Euclidean space. Okay, that's called a Euclidean metric on R squared. And that's the normal distance function. You see? So if I give you 2 points, P1 and P2, and Q1 and Q2 in R squared, sorry, both of them in R squared, then this is called D sub 2 metric because of the powers of 2. Okay, so this is defined to be square root of P1 minus P2 squared plus, P1 minus Q1 squared, and then P2 minus Q2 squared. Okay? Intuitively, you already know this should be a metric because that is the distance on the normal Euclidean space. Okay? Which is the Euclidean distance. If no one, in high school, if they want to find the distance between 2 points, they have to measure it in the Euclidean metric sense. But this is not the only metric that you can define. So I have introduced you some more. So taxi cab metric is D1 metric on P and Q. This is defined to be the absolute value of P1 minus Q1 plus absolute value of P2 minus Q2. And so I really want you to sit down and work it out. So you need to be able to check these 4 properties for these functions. Okay? And always the triangular inequality part is usually the hardest. So do you understand what does it mean? Yes? So if I have 2 points in my Euclidean space, so let me say that this is P1 and Q1, and this is P2 and Q2. So the Euclidean, so P1, what was that? No, sorry, P1 and P2, Q1 and Q2. So what is the Euclidean distance between them? You learned in high school, when I want to measure the distance between them, I measure this length. Okay, so that is D2. But what is D1? D1 measures the distance between the x coordinates plus the distance between y coordinates. Okay, so what happens, the distance between x coordinates, I hope that you agree, that this one is the distance between the x coordinates, and this one is the distance between y coordinates. So D1 measures the sum of these 2 line segments. And of course, the distances are not the same, so you know that the hypotenuse is smaller than the sum of these 2. But you can also prove that this is also a metric. Another metric is called D sub infinity. It's defined to be, you calculate P1 minus Q1, you also calculate P2 minus Q2, and between these 2 numbers, you take the maximum, whichever it is, and that number is called this D infinity. Okay, so it means that in my picture, which one is that? This one. This length is this D infinity. Okay, so it is very clear that D2 is less than D1, and D1 is also, so D infinity is bigger than D1. Do you agree? No, sorry. So D2 is less than or equal to D1, and D1 is greater than or equal to D infinity. Is that right? Okay. But the hard part is to prove the triangle inequalities for them. It's good to sit down and work it out. For example, I have given you another example. So this is simple, we can skip. So this is example 311. So if I have given you this point P, 1 and minus 2, and I have given you Q to be 4 and 2. For example, if I ask you what is the infinity of P and Q, what should I do? I should write the maximum of the difference between x coordinates, absolute value of 1 minus 4, and absolute value of minus 2 minus 2. So this becomes the maximum of which two numbers? 3 and 4. So the distance is 4. Okay. Let us now go to the next one. This one is important. So let A be a non-empty set, and let X be the set of all bounded functions if from A to R. Show that whatever I have defined here for you, as you see on the slide, defines a metric on X. Okay? So let me explain it here for you on the board. This is a very important example in analysis. So this is example 312. So X, so X is, so let me write, A is non-empty set, any set that you like. And then I find X is the set consisting of all functions with domain A and codomain R, but not all of them. The ones that F is bounded. Okay? Bounded, if you want to insist, you don't need to insist, but you can write on A. For example, sine function is a bounded function because the values of sine cannot go beyond 1 and they cannot go below minus 1. So if I want to define a function, if you want, I can define a function f from A to B, if from A to R is said to be bounded if what happens? If the set of values, if its range is bounded. Yes? So the range is a set, and we learned about what is the meaning of a set being bounded last time. Okay? So when I find the range, of course, it makes sense if the range is within R. Okay? If I have a real valued function, a function whose codomain is the set of real numbers is called a real valued function. If f is a real valued function, it is called bounded if its range is a bounded subset of R. Okay? And if it is bounded, we learned last time it has a supremum. Then it means that we can talk about supremum in the first place. Okay, now this tells you that. What is the metric? The metric on the slide. If you give me two functions from the set X, they have defined the distance between these two functions to be the supremum of this set. What is the set? The set is the absolute value of f of x minus g of x. Then you might ask what x is. X is a number from A. Okay? So this is the definition. So does the definition make sense? I give you two functions from G. What do I mean by that? It means f is a function defined on A goes to R but bounded. G is also a function from A to R but bounded. Okay? And then I pick up these two functions and calculate the absolute value of the difference for every x in A. I generate a bunch of numbers in this set, a bunch of real numbers. But if f and g are bounded, it is not hard to show that this value, this set will also be bounded. None of these f's can go beyond the threshold. They cannot go below a threshold. The same happens for g. It is not hard to show that the difference between them, the absolute value of the difference between them, will also remain bounded. If it is remaining bounded, then it makes sense to talk about the supremum. So a supremum will be a number. So we want to show that this is a metric. It's a metric on x. What should I show first? I have to show that these are non-negative for any f and g chosen from there. Do you agree with that? Because this set is a set of non-negative numbers, and supremum is the smallest upper bound. So it is clear that the smallest upper bound cannot be negative. Is that right? So the non-negativity is done. So what about the other one? So do you think that if f and g are the same, do you think I can conclude that the distance is 0? Yes? Because if f and g are the same, can you tell me what is this set then?
0. It's one value, right?
Yes, it is the curly bracket 0, curly brackets closed. It contains only one number in it, and that is 0. And if I ask you what is the supremum of the set containing 0, is just 0. Do you agree? So then it means that this is correct. The other way around, I want to leave it as an exercise. Okay, that's also very simple, but let me do the triangular part myself. So let us say that f, g, and h are 3 functions. F and g and h are within x, and I want to show that the distance between f and g, f and h, is less than or equal to the distance from f to g plus the distance from g to h. I want to prove this. Okay, so how can I prove this? This d is a supremum. I want to show that the supremum is smaller than a given number. So how can I prove that? I would say that let x belongs to A, then what is this distance? This distance, so let me write it like this. Then absolute value of f of x minus h of x is less than or equal to absolute value of f of x minus g of x plus absolute value of g of x minus h of x. Is that right? So you see, it's important to understand how to prove these things. So my goal, my ultimate goal, is to convince you that this is true. But what I have done, I have picked one element, arbitrary element, from the domain of these functions. Fix that number x. And for that number fixed, I am writing this. Do you buy it or not? The absolute value of a number minus another number is always less than or equal to this one, exactly the one I started today with. Yes, this one. Okay? So I hope that you agree that this is true. Okay, but what does this mean? This means that d of f and h is also less than or equal to absolute value of f of x minus g of x plus g of x minus h of x. Do you agree why? Because when I say that this number, whatever it is always greater than or equal to this number, this means that the supremum of these numbers is also, because this means that this is an upper bound for this set. So this means that this is an upper bound of this set. Do you agree? Because you see, I have picked one single element, any arbitrary element from A, and for that x I am calculating this, and I realize that this number is less than this fixed number. This means that this number, whatever it is an upper bound for that one. No, that's not correct. Is it?
It's an upper bound, but not the supermon.
Yeah.
No. It is. So let me. Okay. So now I was a little bit careless. You know why? Because this is not fixed yet. This is fixed for this fixed a. If I start changing x, this left side and right side will change simultaneously. So that was my mistake. Sorry. Yeah. So let me clean this. So this is why I think. Please don't say yes. Okay. So let me clean everything. That was a very huge mistake. But this one I can write it is less than or equal to df of g. This is now correct. Plus dg of h. Do you agree with this one? So you see, I fixed x. For that one fixed x, you have to agree with this part. Yes? Because that is just nothing except a normal triangle inequality. But now momentarily forget about this. Do you agree that this one itself only is less than the distance? Because the distance between f and g is the supremum of these type of numbers. So this means this number, which is one of them, is definitely smaller than the supremum of this set. And for the same reason, this one is one of those numbers within the corresponding set. So this means this one is at most equal to its supremum. Do you understand what is happening now? Now I have the goal. Because now the left-hand side is sensitive to x. By changing x, the left-hand side will go up and down. But the right-hand side is a fixed number. It doesn't depend on x. So this means that I was able to show that. So therefore, because x was arbitrary, it means I was able to show that for all x in A, f of x minus h of x is less than or equal to df and g plus dg and h. So you see, sometimes it is extremely subtle in analysis. It seems that I am doing the same thing, but they are totally different things. The previous one was completely a mistake. It was wrong, but this one is correct. So do you agree with what I have written? Yes? Yes? Okay, but then is this a fixed number or not? Yes, because it doesn't depend on x. It's a number, it's a number. And now what I know, this means that d, f, and g plus d, g, and h, can you complete it, is an upper bound of, I want to wait for you a little bit. What I can conclude from here?
A.
No.
No. No, A is the object.
Because the elements in A are just simple x's. But from this, I can conclude that the number sitting on the right is an upper bound of which set?
Capital X.
No.
Yeah.
Absolute of which set? Because if you cannot complete it, it means that you didn't follow. Then you have to go home and sit down and think about it. Okay? Because we have to cover a lot of things today. So is an upper bound of which set?
Absolute value f of x minus h of x.
Such that?
X belongs to A.
Exactly. Okay? So because you know, where are these elements? These elements are coming from this set. And I realize that every one of them is at most equal to this one. So this means that this is an upper bound for this set. Now, can I conclude this, yes or no, and why? Can I?
Yeah.
Why?
Because an upper bound is greater or equal to the supermon.
And which one is the supremum here?
The left-hand
The
side.
left. Very good. So this means this is correct since D, F, and H is the supremum. The supremum of which set? The same set. Yes? So, this is an extremely important example, okay? Because I have to continue a little bit faster. I really recommend you go sit down and rethink about every step. You see, I was confused myself, okay? Well, that was completely wrong, even though when you compare what I have written before and what is it on the board now, they are very similar, but it is extremely different. So be careful that you really understand what is going on in this example. And by the way, intuitively, can you tell me what distance it measures? Because we are telling that this is a metric. Hopefully you agree with me now. It should measure a distance. What does this measure? And why supremum is important? Could I write maximum here? Could I write maximum instead of supremum? Okay, first tell me what do you think intuitively, graphically it measures? For example, let me draw this graph. Okay, and let me draw another graph. I don't know how should I do that, but something like this. Let us say that this is A, this is B, and this set A is from A to B in this picture. And let us say that this is function F and this is function G. If I ask you what is the distance between F and G, show it in the picture. What is it? Can you show? Because you know that F is a function defined on this set, on this interval. G is also a function defined on the same interval. And you see they are bounded. So they don't go beyond the threshold. They don't go below a threshold. So they are bounded. So according to what I have shown you, this is a metric. It is measuring a distance. But which distance it is measuring?
It's the furthest distance between
the biggest distance.
Yeah, the biggest one.
So here. So I don't know if I can draw it correctly. So this probably is the distance. Okay? And why do you think supremum is important? Could I, in this case, is there any difference between supremum and maximum? This number is also the maximum distance. But it might be the case, if the functions are continuous functions, there is no difference between sup or max. But it might be that the function is not continuous. For example, one point of it is jumping upward. Okay, so let me write it like this. And then another point of this one exactly is hollow, okay? So these are still bounded functions, but they are not continuous. So still I want to give this, I want to entitle this as the distance, but I cannot talk about maximum because the maximum does not exist in this case, but supremum does. Okay, so in the case that I am working with continuous functions, there is no difference actually between max or sup, but in principle, if I don't, here I know that functions are bounded, I don't know if they are continuous. So in general, I cannot talk about maximum, I should talk about supremum. So this metric is measuring the biggest gap between the graphs of two functions. That's a kind of metric, okay? And that's the, exactly, and this is there is a name for this metric. It's called sup metric or uniform metric. That's also good to know. It measures the largest vertical gap between the graphs of F and G. Okay, this is also a good example. So far we have given metric functions, but this is the first time that I have defined a plausible function which seems to be a metric, but indeed it is not a metric. Okay, so I have given you this function. So D from R to R, from R times R to R in this way. Do you think it's a metric? Let us check all the properties very quickly. Is it non-negative? Yes, because the output is some square and it is non-negative. So non-negativity, so 1 is correct. Number 2, do you think it is positive definite? Positive definite means x equals to y if and only if dx and y equals to 0. Is it true or false? If x and y are the same, d is 0. If d is 0, you have to agree that x and y are the same. That's also correct. Yes. Is it symmetric? Yes. Number 3, do you agree that there is no difference between dx and y? Because this is even, I can change it. They are equal. And this one becomes d of y in x. Do you agree? So, but so far it seems it is a good candidate, but suddenly you see that the last one does not work. If you want to show it doesn't work, you cannot prove it, you have to disprove it. It means that you have to bring a counterexample. So can I, for example, let us take x to be 0, y to be 1, z to be 2. Hopefully it will work, okay? So if I take these numbers, let us calculate the distance between x and z, which will be the distance between 0 and 2, which will be 0 minus 2 to power 2, which is 4. But let me also calculate the distance from x to y, which is the distance from x to 0 and 1, which is 0 minus 1 squared, which is 1. And let me finally calculate the distance between, which one? Y and z, which is the distance from 1 and 2. So this becomes 1 minus 2 to power 2, which is 1. Okay? And then you see that when I add them, it becomes 2. So this is not true that the distance from x to z is less than the sum of these two distances. So it doesn't enjoy the triangle inequality. So even though it was more or less close to be a metric, but it is not a metric. Is that right? Okay, so let us see, what do I have here? Okay, it's good to stop here after the break. Okay, any questions so far? Good.